Hello everyone, my name is Eleanor McMurtry. I'm a master's candidate at the University of Melbourne, researching applied cryptography with Vanessa Teague. And today I'm going to talk about some issues that can arise when a test is not actually a proof. So here's an example of something that looks like a proof, but actually isn't. We're going to start with a supposed proof that 1 equals 2. Now obviously this cannot be true, there is something wrong with this proof, but if you go through step by step, this looks like a somewhat convincing argument. Now, the trap laid for the unwary viewer is on line 3, where we divide both sides by a minus b. Now a equals b, so this must be 0, and we are dividing by 0, which is forbidden. So this proof is not actually a proof. Another thing that can go wrong is some kind of mathematical test that we really want to act like a proof, but actually doesn't form a complete proof. Here's an example of the Fermat primality test. The idea is we're going to test whether a number is prime by checking whether any numbers up to that number satisfy a certain equation. And if they do, then this must be a prime number. However, this is not a proof that it is a prime number, it's simply a test. A number that satisfies this may be prime, it is probably prime, but not necessarily. For example, if you choose n equals 341, there's a counterexample, a equals 2, you get 1 mod 341, but 341 is 11 times 31, so it is not prime. This can happen in cryptography too. Our paper demonstrates that a widely cited proof of plaintext equality given to ciphertexts from Jacobson and Newell's in 2000, the paper's called Mix and Match. This proof requires at least one honest participant. Now, the original paper makes this requirement extremely clear. However, many subsequent papers which cite this and use it in their protocols miss this important requirement. And the issue is, this mismatch in assumptions completely undermines universal verifiability. You can't have universal verifiability if at least one of the participants needs to be trusted. A short list of papers that fail this requirement are the famous JCJ paper, and it's also its implementation at Civitas, as well as Pretty Good Democracy, Caveat Coercitor, and a few others that we looked at. There are also a few verifiable auction schemes that make exactly this mistake. It's not just limited to elections, it also pops up in auctions, and I would be willing to bet that it pops up in other domains as well. So the Ewell's Catalano-Jacobson e-voting paper, it's one of the best out there. It's one of the oldest, one of the most carefully thought through papers in e-voting. Has about 645 citations when I checked this. And there's nothing wrong with its verifiability proof. The proof that it has this universal verifiability property, where anyone looking at the result can guarantee it was done correctly, this proof is completely sound and correct. However, it makes a small assumption that without the careful eye of reviewing the requirements, can lead to a catastrophic failure. The components it refers to are completely correct. However, in order to prove verifiability, it requires that the component has universal verifiability. And the paper that it cites is this Jules-Jacobson paper that does not satisfy this requirement. Now, to their credit, they say, we assume the ideal properties of the primitives, and they say that it must have public verifiability. However, the trap lies for the unwary implementer in the fact that the paper that they cite doesn't have this property. So if they follow the paper, implement that test, they're not going to get a correct proof. So again, it doesn't claim to be universally verifiable. In fact, the paper makes it quite clear. A collusion amongst all of the parties performing the test can forge a proof that two ciphertexts are equivalent when they actually aren't. And the paper makes this very, very clear. So let's take a look at how this test is supposed to work. And we're going to look at the Civitas implementation because it's one of the only implementations of a large-scale voting protocol out there. It's one of the only ones we could find, and one of the only ones that gives a nice, complete specification of how its protocols run. It's not unique to JCJ. We believe, based on comments made in other papers, that if authors had done the same thing, done a rigorous implementation and listed out all of the details, they would likely have made the same error. So the way this test is going to work is we've got two ciphertexts and we're working in a subgroup of order Q. So if you raise something to the power of Q, we're going to get the identity back. And there's a few steps to this proof, but I'm going to draw your eye to the important parts. The idea is we're going to test if the quotient of the messages comes out to 1, because if so, they almost definitely were the same message. Now, to hide information about the message, we certainly don't want to leak information about the message. We're going to choose a random blinding factor. Each trustee is going to pick a random Zi, sum them up to get a total of Z. And if M1 divided by M2 is 1, then the quotient raised to that power is also going to be 1. However, if the quotient is not 1, we're raising it to some random large power. That's revealing nothing about the message because the discrete logarithm assumption holds. And with extremely high probability, you're not going to get 1 as a false positive. But hold on a minute. There is a trap here, just like in the proof that 1 equals 2. If all of the tellers work together and make sure that their randomness factors sum up to Q, then we're going to raise the quotient to the power of Q, and we're going to end up with a ciphertext that is 1, 1, the identity ciphertext. And this is a valid encryption of 1. So it's going to pass the test. It's going to make the plaintext look like they're equal when they in fact weren't. This leads to a situation where tellers that collude with each other can include invalid votes and they can exclude valid ones. And this is all going to completely check out, again, because the proof does not have this property of universal verifiability. Now, we discovered that if you added an extra step to the verification procedure, then you could address this problem. Of course, I said, you get the trivial ciphertext 1, 1. So if the verifier checks that the ciphertext does not come out to 1, 1, then the verifier can be fairly confident that there was no collusion and that the test is in fact correct. And our paper gives a formal proof of this property. And thus, we have the trap laid. And remember, JCJ explicitly says, yes, we model it as an ideal primitive that has this property, and they accept, yes, the one that we cite doesn't have this property, but they don't make that explicit. And the same incongruence and assumptions seems to have gone unnoticed in quite a few papers, which I've listed here. These papers, based on a careful reading, don't seem to have noticed that the PET JCJ cites, and indeed almost all of these date back to JCJ in some form. They are extensions or they use some of the ideas, and they don't seem to have noticed this crucial assumption. And again, the issue is not limited only to election schemes. So I'm going to talk briefly about auctions. We mostly studied election schemes, but we did also take a look at auction protocols. Now, the idea of an auction protocol is that you have n participants. Each of them are placing a secret bid. They're going to work together and determine which one of them placed the highest bid and what that highest bid was. And the idea is these auction participants do not necessarily trust each other. They don't necessarily believe that they're all going to be honest. So we need some sort of verifiability where we can argue that the result that is produced is a correct one. Now, we can think of two models. Either each of the participants in the auction should be confident that the outcome is correct, or we can assume this stronger property of universal verifiability, where not only the participants in the auction can be confident of the result, but so can any public observer watching the auction unfold. Now, we noticed that a few papers did indeed claim to have this universal verifiability property. Several of them use a plaintext equivalence test, just like Civitas, and unfortunately, several of them again make this incorrect assumption that the Jacobson-Mules PET, which they cite, is universally verifiable. So here's a short list here. Especially interesting is this work by Collier and Smith, which is really interesting. They talk about converting e-voting protocols into auction ones using Helios, a venerable voting system, as their case study. However, they did not notice this important subtlety and seem to have fallen victim to the same trap. Now, one more thing has reared its head in this research. There is a flaw in Civitas' implementation of the Fiat-Shamir transform. Now, the main idea of the transformation, we're going to take an interactive proof where the prover chooses a commitment, the challenger chooses a challenge, and the prover computes a response that should be difficult to compute without knowing the secret data. This is an interactive proof, and the interactivity makes it quite inconvenient for large-scale protocols. The idea of the Fiat-Shamir transformation is we're going to turn an interactive proof into a non-interactive one. And we're going to do that by generating a challenge, but not just any challenge, because if the prover chooses the challenge and the prover chooses the statement, then it can be quite easy to generate a proof of a false statement. So we need this property called adaptive soundness, and we're going to use the Fiat-Shamir transformation to do that. The idea is you take the whole statement, hash it, and that is your challenge. The hash should be difficult to predict, and it contains all of the information of the challenge, so it cannot be modified later. However, Civitas unfortunately does not hash the entire statement in its proofs, and we're going to see a concrete example of that. So in Civitas, to prove decryption, they use a primitive called EQDlogs, meaning proving that two discrete logarithms are equal. In the algorithmic crypto system, they've got a ciphertext, which is a pair A-B. They compute a decryption factor by raising A to the power of the secret key, and they prove that they really did raise it to the same power that the public key was raised to. And this should prove honest decryption. However, let's take a careful look at step 1 in EQDlogs. When they compute the challenge, the hash does not include the second part of the ciphertext, B. Now notice that the specification I've quoted includes a letter B. That is not the same as the ciphertext B. That is a part of the statement that they have raised to a blinding power. So they haven't included the second part of the ciphertext in this challenge, only the first part of the ciphertext. Unfortunately, we pointed out that this allows a proof to be faked. The idea is you compute a valid proof for some A, and then you choose B however you like to generate a false proof. And this combines with the plaintext equivalence test issue in quite a severe way. Remember that we could fix the plaintext equivalence test issue by checking for the trivial 1-1 ciphertext. However, using this weak Fiat-Shamir transformation, we're able to produce false proofs that look legitimate, that are not going to produce this 1-1 ciphertext. And we can use this in two ways. We can use it both to produce false proofs that equivalent ciphertexts are different, and we can also use it to produce false proofs that different ciphertexts are equivalent, and we don't have this suspicious identity plaintext ready to go. And it's important to point out this is not unique to Civitas. There were similar issues discovered in the Swiss vvote system, and also in Helios, which I mentioned earlier. Both of these systems suffered from a weak Fiat-Shamir transformation that allowed a false statement to be proved. So, to conclude, cryptographic proofs are quite complex. It's quite easy to accidentally undermine their verifiability because the assumptions don't match your protocol. And I really want to stress, the people who worked on these protocols are very, very good at what they do. They are academics who have studied this area extensively, and they still fell victim to this subtle issue. And we found severe examples of this in quite a few influential papers, including one with over 600 citations, both in the e-voting and auction domains, including in a concrete implementation. The moral of the story is that all of your zero-knowledge proofs, all of the implementations you provide for your zero-knowledge proofs, need to include extremely careful verification specifications. They need to explicitly explain This is what you do to verify the proof. This is how you handle corner cases. This is one way that we can try to avoid these issues. We also need to carefully analyze the assumptions and the guarantees that existing work gives us. The assumptions may not be the same as ours, even if they look and sound similar, and the guarantees they provide may actually be weaker than what we need. It's very important that we carefully reread and analyze these issues before we rely on an existing protocol for our new systems. If anyone is interested, here is a list of references that I discussed today.